Hello and welcome to the third video of the M2 chapter, Projectiles. Starter question on the screen as normal. A ball is projected from a point on a horizontal plane with speed 28 meters a second and angle of elevation 30 degrees. Now this is a key phrase. Angle of elevation means that it has been elevated or raised above the horizontal. You might need to know that for phrases you see in your exam. A different phrase which means below the horizontal is angle of depression. Not quite as common, but you might see it. Determine the horizontal and vertical components of the velocity. Okay, so the speed was 28 meters a second and angle of elevation 30. So we just split this into its components. Going along here, I'm going to call this UI, and up here, UJ. So UI, just using basic trigonometry, is 28 cosine of 30 degrees, and UJ is equal to 28 sine of 30 degrees. This one equals 14, and this one cos of 30 is root 3 over 2, so that's 14 root 3. So that's a quick recap of what we did in the previous video. We're going to use this idea together with what we did in the first video to solve problems involving projection at an angle. So when an object is projected at an angle, remember that the horizontal motion and forces are all independent of the vertical motion and forces. Determine all the information in both directions, then apply the constant acceleration formula as needed in both directions. Make it clear which calculations belong to which direction. That's just to help your examiner out. Remember also that when moving freely under gravity, the horizontal acceleration is 0 and the vertical acceleration is g, which we tend to approximate as 9.8 vertically downwards. The rest of the video is lots of examples bringing together the work we've done from the last two videos. So here we go. A particle is projected from a point O on a horizontal plane with speed 28 and angle of elevation 30, that's what we did in the starter question. After projection, the particle moves freely under gravity until it strikes the plane at point A. Find these three things: the greatest height above the plane, the time of flight, and its distance from the starting point to the point it hits the plane again. I'm going to do each of these on a separate screen. The greatest height above the plane reached by the particle. Okay, so we've got a horizontal plane. Particle here at O is projected 30 degrees at 28 meters a second. And of course that straight arrow is just representative of the initial velocity. An instant after it has been projected, it is then on a parabolic trajectory. It comes down and hits the plane again at A. For this question, we want the point of greatest height. Greatest height above the plane reached by the particle. We want to know how far is this. And this has absolutely nothing to do with the horizontal motion. This is all about the vertical motion, which is quite nice. It means that we can take our vertical speed that we had for the initial speed. That was 14 from our starter question. So this is uj, and the vertical velocity at greatest height, I'll call that vj, we know from our M1 work that that must be 0, the vertical velocity. We also know the vertical acceleration, of course, is still 9.8 downwards. So if I resolve this now, I will resolve in the upwards direction. Then the initial speed is positive 14. Acceleration is down, so that's negative 9.8. And the final velocity at the point of greatest height is 0. And we want to know how far is that, so s, the displacement. Here we're going to use v squared equals u squared plus 2as, but in the numbers we get 0 is equal to 14 squared plus 2 times minus 9.8 times s. If we do that calculation, we get a very nice number, 10 meters. Part B, we need to find the time of flight of the particle. So here's our horizontal plane again. We're starting here, projected, same as before, trajectory down to point A, and same as before, we only need to consider the vertical motion here, because if we want the time of flight, how long does it take to go up and back down, even though it's moving horizontally as well? That's all about the vertical motion. So if we put a few key things on here, vertically, again, initial speed is 14. We know, of course, the acceleration is still minus 9.8 vertically, and by the time the particle gets over here, the vertical displacement is 0. So I could call that Sj, I guess. What you might think of as the y coordinate. Starts at 0 here, and goes up, comes back down, and hits 0 again here. And the question is, what is that time? So if we resolve vertically downwards this time, not for any particular reason, just to show that you can. So we've got u is equal to minus 14 now, a is equal to 9.8, s is equal to 0, and t is the thing we want to find. Now we're using s is equal to ut plus a half at squared. If s is 0, we get minus 14t plus a half times 9.8, 4.9 t squared. As you might expect, we can factorize out the t here, and that will give us one answer as t equals 0, which of course is where it starts. What we want is the other t, the time where it comes back to this same level. So that's here. We've got t is equal to 14 divided by 4.9, and that gives us a decimal answer of 2.86 to 2 decimal places. Finally, part C wants the distance OA. Now here we've got the time. I will use the fraction value of 20 over 7 to keep an exact value for the t there. We're going to use that in this next part. So if I put on here t is equal to 20 over 7 seconds. So we've got our projectile coming off, here it comes, and this is striking at point A, it starts at point O, and they want the distance here, the horizontal distance, OA. So now of course we are looking horizontally, and horizontally we know that the initial speed, if I call that ui again, was from our starter question, 14 root 3 meters a second. We know the time, 20 over 7 seconds from part B. We can now just do a simple calculation of speed times time. If I put it in the usual format though, let's say resolving to the right, a is equal to 0, t is equal to 20 over 7, u is equal to 14 root 3, and we want s. S is equal to ut plus a half at squared, where a is 0, this becomes 0. So s is equal to 14 root 3 times 20 over 7. And that gives us a final answer of 40 root 3, or in decimal form, 69.3 to 3 significant figures, meters. And that is our final answer for part C. Second example. A particle is projected from a point O with speed v meters a second and angle of elevation theta, where tan theta is 4 over 3. So actually, let me just write straight away from that. Tan theta is 4 over 3. I can say that sine theta, remembering that tan is opposite over adjacent, and this is a 3 and a 4, so the hypotenuse there will be a 5. Opposite 4 over hypotenuse 5, using the same idea that we had in our previous video, sine theta is 4 over 5, and cosine theta is 3 over 5, adjacent over hypotenuse. So from this information, I've got these two bits straight away. The point O is 42.5 meters above a horizontal plane. So it's above a horizontal plane and it's being projected upwards. This is one situation where it might have been projected downwards, but it isn't. So here's our particle. It's being projected upwards with an angle of elevation theta and a speed capital V. This is 42.5 meters high, and its trajectory will be parabolic in shape. We're also told that the particle strikes the plane at a point A, so this is A here, 5 seconds after it is projected, so t equals 5 at this point. Show that v equals 20 and find the distance OA, where this point up here is O. In an exam, of course, if you got stuck showing that this was true, you could still just use that value to find the next part. So show that v is 20. To do this, I'm going to resolve vertically, because here I know the displacement from O to A, the vertical displacement, is 42.5. I know the acceleration, of course, and the time, and I want to know the initial velocity. So I know 3 things, and I want a 4th. So resolving, I'm going to resolve upwards as positive. So A is going to be minus 9.8. The displacement is also going to be a negative, because from this point to this point it has gone down 42.5, and if I'm making up my positive direction, then that must be a negative. T, of course, can only be positive, that's 5. Now the initial velocity is the thing that I want, but that is not v, because this is not vertical. What I want is the vertical component of v. So let me put this in purple here. So this would be v sine of theta. And we do know sine theta is 4/5. Now it's a shame that they've used v in this question, because this is actually our u. The initial speed is capital V sine theta, which is 4/5 of capital V. Now the formula we're going to use is S equals ut plus a half a t squared. Put all of the information in. Minus 42.5 equals 4/5 of capital V times time, which is 5, so they cancel. Plus a half times minus 9.8, that's a half minus 9.8, and t squared, 5 squared. Solving this equation gives us v is equal to 20, which of course should not be a surprise because they told us that in the question. So that has been shown to be true. Now find the distance OA, and as I said earlier, this is a little bit easier, because if v is 20, this is v cosine theta, which is 20 times 3/5, which is 12. So when we resolve to the right, we know a is 0, u is 12, t is 5, s is the thing that we want, s equals ut plus a half at squared. And as we've seen a few times now, that disappears, and we get 12 times 5, which is a nice round 60 meters. Now I have to admit that I have fallen into a classic mistake and finished the question before it was really finished. I was so focused on getting to this point here that I neglected to realize that this is not what the question is asking me to do. I have to do this as part of it. That is this distance here, the horizontal displacement, but what the question is actually asking is the distance from O to A, this diagonal distance in red. And that's really easy, obviously. OA is just equal to the square root of 60 squared plus 42.5 squared, and that gives me a final answer of 73.52 ... which is 74 meters to 2 significant figures. And that is the final answer for this question. Now when you come to see this screen later on in the video, you'll notice that nothing in red is on that screen, because this was a later edit when I realized that I had not actually finished the question. So be careful on that. It's an easy thing to do and an easy way to lose marks in an exam. The next example is a little bit different. A particle is projected from a point O with speed 35 meters a second and angle of elevation 30. The particle moves freely under gravity. Find the length of time for which the particle is 15 meters or more above O. So So a good diagram here is quite useful. We're going to have our point O here. It's projected out at 30 degrees to the horizontal. It can move freely under gravity. We don't have a plane that it hits, so potentially it continues falling. But what's interesting about this is that we are considering everything relative to the point O. So although it's not on a plane, this is our point of zero vertical displacement. And the question is, find the length of time for which the particle is 15 meters or more above this vertical plane here. So 15 meters above this, let's say that's here. Where of course these are parallel, so this is 15 meters over here and over here. And we want to know what is the time the particle takes from here, going up, 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 down, 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 back down to here. So what is this time here, and what is this time here? Then if we know this time and we know this time, we can find the difference between them just by doing this minus this. So this is another situation where the horizontal motion doesn't really affect anything. We're looking mostly at the vertical process. Starting here, whatever the vertical speed is, it goes up, comes to an instantaneous stop at the top, which would be here, and then it starts to fall back down again. And we're interested in the time it is above 15 meters. So let's look at the vertical. We're resolving, I'm going to go upwards as positive. So A is minus 9.8. The initial speed is 35 sine of the angle, 30. And sine 30 is just a half, so that is 17.5 for U. The point we're interested in is 15 meters above O. So I'm going to put S is equal to 15. When does that happen? Time is what we're interested in. And our equation is S is equal to ut plus a half at squared. And here we can see the value of having a quadratic, because in this situation we're going to have two non-zero values for t. 15 is equal to 17.5t minus 4.9 t squared. Now these numbers aren't the nicest numbers in the world, but if I just leave them as they are and rearrange this into a normal quadratic form, and then I can solve it with the quadratic formula. T is equal to 17.5 plus or minus the square root of 17.5 squared, minus 4 times A times C, all divided by 2 times A. That gives me two values. The first one is 10 over 7, and the second one is 15 over 7. And I'll leave those as fractions until I finish my final calculation, which is just to subtract t1 from t2. So we've got 15 over 7 minus 10 over 7 is 5 over 7 seconds, and as a decimal, that is 0.714 seconds to 3 significant figures. And just as I've written that, I've noticed that I have made a slight mistake on not only this example, but a previous example as well. And that is in the number of significant figures I've used in my answer. There, and also here. I shouldn't really be using this many significant figures, although I labeled it decimal places at the time, because I've used a rounded number in my calculation, which was A. A is equal to G, and G is only approximately equal to 9.8 to two significant figures, and I shouldn't give an answer at greater accuracy to the values that I've used in the calculation. So let me correct that here and write instead 2.9 seconds to two significant figures. And that does have a slight knock-on effect here as well, because although I didn't use G in this calculation, this value here has come from a calculation that used G as 9.8. So unfortunately, I should be changing this one as well. 69 meters to two significant figures. See, were there any others? Those two were okay. And this is the one I've just done. So that should really be 0.71 seconds to two significant figures. All of that because of using 9.8 instead of, for example, 9.81, or something more accurate. One final example. A ball is struck by a racket at a point A, which is 2 meters above horizontal ground. Immediately after being struck, the ball has velocity this, and travels freely under gravity until it strikes the ground at a point B. Quickly showing what this is, we've got a point here that's being struck with 5I and 8J, traveling freely under gravity, so it's parabolic, and it's coming down below the point it was struck because this is 2 meters above the ground. Striking the plane here at point B, it was struck here at point A. A nice thing about this example is the velocity given in this form is already split into its components, 5 and 8. So the greatest height above the ground reached by the ball, similar to the first example, we're going to be looking at resolving vertically. Taking upwards to be positive gives me minus 9.8 on my acceleration. The initial speed we know is 8 vertically. I want to know the greatest height, that's when the vertical velocity is 0, and I want to know the displacement from A. We've got v squared is equal to u squared plus 2as. 0 is equal to 64 plus 2 times minus 9.8 times s. That gives s as 160 over 49, or in decimal form 3.265 ... Now I won't round that just yet because I haven't quite finished. This is a little over 3 meters above the point A, but the point A is itself 2 meters above horizontal ground. If I go back to this diagram for a second, that's saying that this distance here is 3.2 above A, but I also need to add on this 2 here. So the total height above the ground, not above point A, above the ground, is actually that answer plus 2. To make that clear, I'll make a little statement here. Greatest height above ground, or the ground if I wasn't being so lazy, is 3.265 ... plus 2 equals 5.3 meters. Two significant figures. For the reason mentioned previously, we've used 9.8 in the calculation. So 5.3 to two significant figures is the answer for part A. Part B, the speed of the ball as it reaches B, and also the angle of velocity the ball makes with the ground as the ball reaches B. Now these two kind of come together because they're both talking about the velocity as it hits the ground. So if I skip back to the diagram to talk about this just for a moment, that is when it's coming down here and it is hitting the ground with a certain velocity this way. As with the initial velocity, to find this velocity, you put together the I and the j component, and then you can use the inverse tan to find the angle. We're going to do the same thing down here. If I make this arrow a little bit longer, then we can see a little bit more clearly. We're going to find the horizontal component of the speed at this point, the vertical component of the speed at this point, and then put them back together. The angle I'm going to look at is probably this one here. I'll call this one theta. I'll call this v, this can be vi, and this will be vj. Before I go back to the question screen, let me quickly note that vi is by far the easiest part of this, because without any horizontal acceleration, it's still 5. The horizontal velocity does not change as this ball moves freely under gravity, so vi is equal to ui is equal to 5. And we'll find vj by resolving vertically, in doing that calculation. Okay, let's get to it. Resolving to the right, I can simply say Vi is equal to Ui is equal to 5. Now resolving vertically downwards, we had the initial speed as 8, but it's going upwards, and if I resolve downwards, that is now considered a minus 8. A is equal to 9.8, that's moving downwards. At the point at which the ball hits the ground, it has a vertical displacement of 2 meters downwards. It started 2 meters above the ground, it's finished on the ground. So this has a 2 meter displacement downwards, so that's positive. And what we want is the velocity. So V squared is equal to U squared plus 2AS. That gives us 64 plus 2 times 9.8 times 2 is 103.2, and then square root that to give 10.158 ... meters a second. And that also is acting downwards. We can see by the fact that it's come out as a positive number downwards. So if we've got 10.158 ... going downwards and 5 going to the right, we need to put these back together using Pythagoras to find our final speed, v. So v is equal to the square root of vj squared, which brings us back to 103.2, plus 25 from our 5 squared, and that equals 11.322 ... And again, we should round that to 2 significant figures. The last thing to consider is angle theta. I'll choose this one here, so I can say angle to the horizontal, and that is, as usual, tan of, so we've got 10.158 ... divided by 5. Put that on your calculator, and that gives 63.79 ... which is 64 degrees to 2 significant figures. And even though I've put it on my diagram, I'm just going to add on there to the horizontal to make my examiner smile. And there we go. Many examples there of using these ideas in slightly different ways to find slightly different things. That should be plenty for you to have a go at some of the questions in exercise 1C. Maybe I'll see you in the next video for some generalization of this and making some formulae.